Hello. Oh, okay. I don't know if this is recording, but I'm going to have faith. Right. Welcome to another nostalgic math ramble. Let's ramble. We are looking at the department's May 2023 paper 1, and we're looking at question 7.3. Let's get into it. The graph y is equal to f prime x has a minimum turning point at 1 and -3. Determine the values of x for which f is concave down. Okay, so I think we're being asked to assume that this turning point we've been given is the only turning point that the graph has. So essentially then it's a parabola of some kind. So let's say this is our axis. We are told that there's a turning point at 1 and -3, so over here. So this is potentially a parabola that looks like this, right? And very important, this is the graph of the first derivative of x, not of f, the function f, the first derivative. And remember, the first derivative tells us about the gradient of the function f, or the graph of f. Okay, so from this information, we can draw an image of f, or a potential image of f. So what we are interested in is, what we are interested in is the concavity. So concavity is given by f double prime, right? So the derivative of this guy. And what we know is when f double prime is smaller than 0, then the graph is concave down. Okay, let me just double check this. So I know for a fact that y is equal to x squared is concave up, and first derivative is 2x, second derivative is 2, which is greater than 0. Okay, so yes, my intuition is correct. If the second derivative is smaller than 0, if it's negative, then the graph is concave down. And then similarly, when f double prime is positive, then the graph is concave up. Okay, right. So in this case, we have been told about the graph of f prime x. So in order to figure out what's happening with f double prime, we're going to have to look at the first derivative of f prime, right? Because the first derivative of f prime is f double prime. And remember, first derivative of a function tells us about its gradient. So essentially what we are looking at in this graph, in this graph, we are looking at the gradient. What is the behavior of the gradient? Because once we know the behavior of the gradient, then we know the behavior of f double prime, because that is the first derivative of the first derivative. I hope that makes sense. Okay, so let's talk about what's happening with the gradient. So we see that the gradient is negative until we get to x is equal to 1, where the gradient is 0. Remember, at a turning point, the gradient is 0, because if you drew a tangent there, it would be a flat line, right? So then when x is equal to 1, we have a 0 gradient, and then after that, we start to have, okay, so maybe let's do that just to show the different phases. Then after that, we have a positive gradient all the way, okay? So essentially what we're saying is when x is less than 1, right, then the gradient of this graph, which is the double derivative of f, is going to be, it is negative, right? And then when x is equal to 1, then the gradient of this f prime x we saw is equal to 0. And then when x is greater than 1, the gradient becomes positive. Okay, and so this is us talking about this graph, the graph of f prime x, which is why f double prime x in this context is talking about gradient, right? We're talking about it relative to f prime x. But now the question tells us to talk about the concavity of f, right? So now when we look at f prime x, f double prime x, relative to f, it is now talking about concavity. So relative to f prime x, it's talking about gradient because it's the first derivative of f prime x. But relative to f, because it is the double derivative of f, then, or the second derivative of f, then it is telling us about concavity. All right. And so what we can then say is, oh, what does it say? Okay, well, let's just talk about it in general, then we'll answer the question. So what we then know is, we don't know where my pen is. Okay, so we then know that when x is greater than 1, then f double prime x is positive, okay? And we know that when f double prime x is positive, then f, right, very important, not f prime x now, f will be concave up, okay, because its second derivative, we've just seen its second derivative is positive whenever x is greater than 1. Then we know that when x is equal to 1, okay, let's change colors. When x is equal to 1, f double prime x is equal to 0, right? And that means that at that point, because we definitely don't have, well, we haven't been told, so yeah, when x is equal to 1, we know that, okay, so what I'm trying to figure out is, okay, we know that sometimes we have situations where f prime x is equal to 0 and f prime prime x is also equal to 0, in which case we know that this is a turning point because of this. But if we have a situation where f first derivative f prime x is not equal to 0, but f double prime x is equal to 0, then we know that we just have a point of inflection, right? So a point of inflection being, it's not a turning point, so it's not a place where the gradient goes from negative to positive or vice versa, but rather it's a point where the gradient remains positive, but there's just a change in concavity. So it's something like, whoops, not like that. So it's something like that, guys. So it's something like that, where you can see the gradient has remained positive all the way, but there's a part of the graph where the first part is concave down, but then the second part becomes concave up. So that guy over there is what we call a point of inflection. Okay, anyway, so what I'm trying to figure out is, okay, can we say that when x is equal to 1, when x is equal to 1, we have a point of inflection, or is it a turning point? And we can say that it's a point of inflection because what we've seen is that f prime 1, so the value of f prime when x is equal to 1 is equal to negative 3, which is not equal to 0. So therefore, there isn't a turning point in the graph of f when x is equal to 1, right? It won't be a turning point. It will in fact be a point of inflection. Okay, so we're just going to have a situation where the concavity is changing. So over here, when x is equal to 1, we'll have a point of inflection. Okay, so that means the concavity will just be changing from the one to the other. Okay, right, so that's that. Right, the last bit is that when x is equal, well, when x is smaller than 1, we saw that the second derivative of f is going to have negative values. So that means that when x is smaller than 1, the graph of f is going to be concave down. Okay, so that means we're going to have a graph that's kind of like the one I just drew, where it's concave down, and then when x is equal to 1, there's a point of inflection, and then it changes to concave up, something like that. Okay, so just to then return to the actual question, determine the values of x for which f is concave down. So that will be these guys over here. When x is smaller than 1, then our second derivative is yielding values that are smaller than 0, i.e. negative values, and therefore the graph of f is concave down. Let's see what the memo has to say for itself. 7.3, yes, x smaller than 1 is our answer.